Bernoulli rule type 3. So type 3 means you get indeterminate forms infinity minus infinity. So that's a type 3. So sometimes the Bernoulli rule sometimes also called by the L'Hopital's rule, which is a historical mistake because this rule was obtained by Bernoulli. So let's look at the how we're gonna proceed. So you can see, so you get problems that's going to bring it to infinity minus infinity situation. So there are a few steps. The first step is we're gonna use the basic algebra to simplify. So what we can do, we're gonna simplify the fraction to bring it to either 0 or 0 or infinity type. And next we can use type 1 or type 2 arguments to find the limit. So next use a type 1 or type 2 methods to find the limit. So let's look at a problem. Suppose we have limit x goes to 0 plus 1 over x minus 1 over sine x, and we know the graph of sine x, so which is like this. So it's going to go through 0 and go like that. So that means when x goes to 0, sine goes to 0. That means 1 over sine goes to infinity. So you can see this is a infinity times infinity problem, because 1 over x also behave like this. 1 over x have the graph like this. So that means when you go to 0, this part goes to infinity. Next, what we do is we simplify the fraction. So we can use a 3a argument. So what's a 3a argument? We're gonna multiply using 3 arrows. So there's a this way and that way, and then also the bottom. So we call this is 3a argument. So we can do that. So that means first, so we're gonna write the same limit. So it's a limit when x goes to 0 plus no change to that. Next, what can we gonna do? We're gonna multiply this way. So when you multiply this way, it's a 1 times sine x. So it's gonna be sine x. And then we're gonna multiply this arrow. It's a 1 times x. So this is going to be x divided by the bottom. So you're gonna multiply these two in the denominator. So you're gonna get x sine x. So that's the first step. You're gonna just simplify the fractions. So using the 3 argument. Now what we do, once you do that, you can see the top is going to be a 0 minus 0. So it's a 0 minus 0, so it's a 0 divided by bottom is 0. It's a 0 0 problem. Right after we do that, you're going to go to a 0 0 problem. That means we can use the Bernoulli rule here. So that means we can look at the derivatives of the top and the bottom separately. So derivative of the top, sine has a derivative cosine minus 1 divided by, here we have to use the product rule. So what's the product rule? Take the derivative of the first one, multiply by the second one, and then plus take the derivative of the second one, which is cosine x, times multiply by x. So now you check what will happen when x goes to 0. And you can see that when x goes to 0, so here we use the property sine 0 equals 0, and you can see that when x goes to 0, cosine 0 is 1. So because of that, you again get 0 0. You again get 0 0. That means we take the derivative again. So let's take the derivative again. So when you take the derivative of cosine, which is negative sine, and in the bottom cosine becomes sine becomes cosine, and here we have to use next we have to use the product rule. So let's take the product rule. So take the derivative of x, which is 1. So 1 times cosine x, and the next one what we can do, x times the derivative of cosine, which is negative sine. So now let's see what will happen again. So when x goes to 0, again the numerator is 0, and the denominator, you can see you're going to get 2 in the denominator now. So we have So actually we can pull the negative sign out and write it like this just to simplify it. So you can say this is 0 plus, this is sine, and in the bottom you have 2 cosine plus, actually it's a minus x sine x. Now when x goes to 0, this goes to 0, uh, this whole term goes to 0, but this goes to 1. So because of that you get 0 over 2, which is 0. So the final answer is 0 for this problem. This problem can be a little lengthy because of the algebra involved. So let's look at another problem. say we have this problem now. Limit x goes to 0 plus 1 over x plus ln x. So, and you know that when x goes to 0 plus 1 over x goes to infinity, and ln x goes to negative infinity from the graph of natural log. So this is a infinity minus infinity problem. That means a indeterminate form. So this is a infinity minus infinity problem. So that means what we do, we need to do algebra here. So what's algebra here is we just simplify the fraction. So x goes to 0 plus, and you can write this one as ln x over 1. So it's just a cross multiplication. So that means you're going to get it's a 3a argument, 3 arrows. So it's a 1 times 1, so you get 1. And then x times ln x, that's the second arrow. And then the bottom is x, so that's what you get. And you need to put a parenthesis around. Actually, for this one, you don't need a parenthesis because the fraction is a one term. If there are two terms, the first one you have to put a parenthesis. Okay, anyway. So now what we normally do is we take the derivative, but and then you know, like earlier in type 2 problems, we showed that x ln x goes to 0 when x goes to 0 plus. So that term goes to 0. So if that term goes to 0, top goes to 1, the bottom goes to 0. So clearly this one goes to infinity. So this is going to be a positive infinity problem. So answer is positive infinity. But if you don't have the problem, you know, remember, like I should remember that result when x goes to 0 plus x ln x is 0. So that's like a result that we can remember. And from this result, and you can plug in here and then you can show that. But if you don't do that, what you want to do normally is you have to find that limit first. So you find x ln x first, and then we use that here and get the answer. So so I'm going to give you a few more problems for you to try. So why don't you try this one? Let's say I'm going to give this as an exercise. Try to do this one. So let's say limit x goes to 0 plus 1 over x minus 1 over tan inverse x, or arctan. So try to do this one and see whether you get a 0 as the answer for this problem. Okay, so very similar approach. You might need to remember this one, the derivative of the tan inverse function is the inverse tangent. It is 1 over 1 plus x squared. So you might need this result. So this is very similar to the first two problems. So you can try this and see whether you get 0 as the answer. Okay, so let's try another one. So we have limit x goes to infinity x minus ln x. So again, if you remember the graph of natural log, so you can see that it's going to grow like that. So that means when x goes to infinity, and you can see that the y value also goes to infinity. So that means this is a infinity minus infinity problem. So now the problem is like in earlier problems, you remember, like, you know, we simplify the fractions, but now there's no fraction to simplify here. So like we kind of get stuck here. So what we can do, like we do a special trick for this problem. So we try to bring this to the form by doing this. So it's a limit. It is x goes to infinity. What we do, we pull x out as a factor. We pull out x as a factor. Right after you do that, you can see this is 1 minus ln x over x. So that's what happened. And then once you do that, so you can see earlier we proved that in type 1, we proved that ln x over x goes to 0. Because ln x always grows slow compared to other functions, compared to polynomials, compared to x, compared to ex, like that. So this is a problem. So if you don't have this result, you have to prove that first. So but remember, this as a result is a very important result. So it goes to 0. Since that goes to 0, you can see you simply get is so you can see that it is simply limit when x goes to infinity, you get x times 1. So that means when x goes to infinity, this goes to infinity. So it's like a really nice problem. And remember, like how we prove this one. We first pull x as a factor, and then we like a really nice argument using the fact that so we use this result. So we use the result that limit when x goes to 0, ln x or x, actually in this case it should be x 0 plus, otherwise ln x is not defined, is 0. So we used this interesting result from in an early result in type 1. Okay, so this is the answer. So it is infinity. So let's look at the last problem of this type. As the next one, we have limit x goes to infinity, square root of x squared plus 6x plus 1 minus x. So if you get a problem like that, what we normally do is we use the conjugate method. So what we do is we're going to multiply by the conjugate. But right after you multiply by the conjugate, what will happen is simplify really well, and then you get a fraction, and then you can find the limit of that fraction. You might have to divide the top and bottom by x again, but you can do that. So, but in this one, we try to use the Bernoulli rule and see how we can do this problem. And you can see that again, when x goes to infinity, the first one goes to infinity, second one also goes to infinity. So it's an infinity minus infinity problem. And again, it's infinity minus infinity, but there's no x term here. So there's no way you can bring it's not you don't have a simplification here. So as in the previous problem, we do the same trick. We try to pull a x term out. So that's the trick. We pull x term out. But once you pull x term out, what does that mean? That means that you divide all the terms. So you pull x term. So but when you pull x term under square root, what you do is you actually divide by x squared. So that's what happened. When you pull under square root, you actually pull x squared. So it's x squared under square root because of the square root term. Minus the other one is fine, so you get 1. So that's what happened. So you had x squared term. Now, and you can see right after we do that, so what's going to happen is, so the first term actually, you can see it goes to infinity. But the second term, if you look at the second term, the first one goes to 1. So it's like a 1 minus 1 situation. So it becomes 1 minus 1 situation. That means the second term goes to 0. So it's a 0 times infinity problem. So if you have a 0 times infinity problem, you know what to do. That's like a type 2. So when you have type 2, what we do, we're going to bring the easier one down. That means we can write this one as limit x goes to infinity. So if you divide the top and bottom, and also we can simplify a little bit of algebra. So you can see the top now becomes 1 plus 6 over x plus 1 over x squared square root minus 1 whole thing divided by, so you're going to get 1 over x. So that's what you get. And and then you can see once we do that, what will happen is this is going to be a 0 over 0 problem. So since the 0 over 0 problem, what we're going to do is we can take the derivative now. So let's start with the derivative. So you're going to write the limit part first. So limit x goes to infinity. So it's a 1/2 power. By the chain rule, it is 1/2. And then 1 plus 6 over x plus 1 over x squared to the negative 1/2 times the derivative of the inside function, which is negative 6 over x squared by the power rule. And then the other one is negative, you can see 1 over x cube, again by the power rule. And how we do it, because you know that you can write 1 over x squared as x to the negative 2. And we can also do one more trick actually. To simplify this one, you can also multiply the top and bottom by x squared. When you multiply by x squared, not x cube, I multiply by x squared. Why you do that? You try to get the 1 in the denominator. That's the goal. Once you do that, 1 over x squared term get cancelled out. So that means this is 1. And then from the numerator, you can see that you're going to get 6 plus 2 over x, and then divided by the square root term going to come down because you can see it is a negative one here. So it is 6 over x plus 1 over x squared square root. Now clearly when x goes to infinity, the 6 over x goes to 0, 1 over x squared go to 0, 2 over x go to 0, so that means you simply get 6 over 2, which is 3. So you get the 3 as the answer. So that's how you do a problem like this using the Bernoulli rule type number 3. So next in the next video we can talk about Bernoulli rule type number 4. That's like a little complicated ones. All those are log functions and stuff like that. So that's like a log limit problems. Yeah. So let's meet in the fourth video. So thank you so much for watching.